Welcome to day 20 of the Advent of Code. Today is all about assembling a large image from smaller tiles, which are randomly rotated and flipped. Here you can see an example of such a tile in our input. So every tile has a unique ID. And then for educative purposes, I show you that they consist of a border. Those are the characters here at the border. And then the stuff inside is the payload. Okay, so we have a 10 by 10 tile, but only the 64 characters in the middle are the actual payload. What do we need the border for? So for every tile, we can uniquely determine all the neighbors. So for example, we could say at the top we have this border, and the tile above us at the bottom will have the same border. Okay, and so we can stitch the original image back together. Okay, cool. So here's the parsing. Again, regular expressions, tile with the ID, and then lots of characters and line breaks. And here I use the border function to extract the border from these images. For example, here I say the top border starts at index 0 and extends up to but not including index 10, and I want to step 1 each time, so we can provide a step. And here we simply pass these parameters on to the range function, and I didn't always know that you can even provide a step. By default it's 1. Okay, and then we map the char function over the range and then join the string. That's also a quite nice function for string stuff. Okay, and we do that for other borders as well. For example, the bottom border starts here and goes 1 to the right, whereas the left and right borders start here and go 11 for the step, right? Because that's the stride of our image, 11 due to the line breaks. Okay, and then the payload, we extract 8 substrings from the original string. 11 means we start here. Okay, and then we use substrings from 1 to 9, so that would be this guy. Okay, cool, so that all works. Then now what about all that rotating and flipping? I simply wrote 2 functions for that, where I provide a original tile, and then it will give me back a rotated tile or a flipped tile. Rotates 90 degrees to the left, and if you think about it hard enough, you will come up with these formulas basically. And then for the payload, we need a different interesting mathematical formula to extract the characters in the right order. For example, here we start x. Let's see if I can explain it to you. We start x in the payload. We start x here, and then we move x down in the outermost. I'm sorry. We start x here, move it to the left in the outermost loop, and move y down in the innermost loop. Okay, and that's why we get the characters in the correct order for the rotated left by 90 degree version. Okay, and flipping is even a bit simpler, so only left and right change with reverse. Top and bottom are assigned to each other, and the payload can be constructed via substrings. Okay, so that's not too hard. And then the symmetries function simply takes an original tile and then computes the rotations by 90, 180, and 270 degrees. That are the first 4 symmetries, and the last 4 symmetries are just the flipped versions of those. Okay, and that should be all the symmetries. Okay, and then for part 1, I wrote helper functions first. So this helper function find neighbor says, starting from an origin, I want to find the neighbor in a certain direction, and I have to pass in the opposite direction, for example, left, right, or bottom, top. And then we simply filter all the tiles for a tile that, where our own direction matches the opposite direction of the tile. And this will give us 2 tiles, a real useful tile, and then another tile where the IDs are the same because we've just found a symmetry of ourselves. And of course we don't want that. Right, that's where have I ever shown you not equals. I think that's a lot more readable than, this guy from other languages. Okay, right, and then I know that this will only give us a single result. I could call first on that, but I think it's nicer to make this with sequential destructuring. Okay, so that's the only real neighbor. And then find edge calls find neighbor once, and if a neighbor is found, otherwise this will return nil if it's not found. We recur with the neighbor as the new origin. So this will basically walk to the edge in a certain direction by repeatedly calling find neighbor. Okay, and then here we have already the solution to part 1. So we start with a large input, pass the tiles, and then we mapcat the symmetries. So mapcat is just a combination of applying map first and then applying concat. So I don't get nested sequences. I don't want the symmetries in their own sequence. I want them to be flattened out. So instead of mapcat, you would say flat map in Scala, for example. Okay, then I have this huge tiles collections with all the symmetries now, and I simply pick the first one, and that's a tile somewhere in our large solution. We don't really know where it is. Okay, but then starting from somewhere, we find the edge to the top. Then we have some tile at the top, and then starting from that some top, we go to the left and to the right. Then we have the top left and the top right. And from there, from top left and top right, we go to the bottom, and then we find bottom left and bottom right. And all we have to do then is multiplying those 4 tile IDs. Okay. Right, and note how the code layout matches, top left is at the top left in the source code, top right and the top right in the source code, and so on. I think that's cute. Okay, so note that we don't even assemble the complete image, right? We simply walk through an unknown territory and find those 4 tiles. We don't even look at all the other tiles. That's quite interesting, I think. Okay, and then for part 2, we do have to assemble the complete grid. How do I do that? So again, we start somewhere, compute some top and some left, or top left. And then I compute the complete left edge with some interesting function. Maybe let's start here. So iterate takes a function and a starting value and repeatedly applies the function to that starting value. So I say I want to start at the top left and then repeatedly find the neighbor to the bottom. Okay, and sooner or later that will bottom out and only give us nils back. And to prevent that, we pass the sum function, which is just the opposite of the nil function, to the take while function. So that will cut our infinite sequence of nils off, and we get a finite sequence of length 3 or 12, depending on the input. The real input will give us 12 tiles. Okay, and then I loop over that left edge, so that's the leftmost tile in some line. And then I do the same thing again, but now we find the neighbor to the right. Okay, so then tile will be, we'll loop over all the columns in all the lines, basically. Yeah, I think that's quite nice. And this will give us a 2-dimensional sequence, because I really want a 2-dimensional grid. If I had, removed this inner 4 and simply had 2 bindings for a single 4, then I would have ended up with a 1-dimensional sequence of tiles. Just to explain the difference. Okay, and then the next function, assemble image. What does that do? Now we have 3 nested loops. So we loop over all the lines. Then we loop over all the y values in our payload, and then we loop over all the tiles. So getting this right also wasn't trivial for me for some reason. So looping over nested 2-dimensional structures, it is what's a bit non-trivial here. Okay, and then at the payload of the tile, we look at the substring, and that is then joined again. Okay, cool. So that also works. So then we get a large string. And then we are supposed to find this monster in the large string. Okay, so it looks like Nessie from Scotland or something. So all these spaces mean it doesn't really matter what's in the image there. We're only supposed to look for those pound signs. So when those pound signs appear, at the right distance from one another, then we have found a monster. Okay, and there are multiple monsters in our input. Okay, so I solved that with regular expressions. I said all these spaces, if it doesn't really matter what's in the input, let's use dots for them, because dots mean anything in a regular expression. And then all those dots, I group them with, regex groups. Okay, and then we have the pound sign. So I hope you can still identify the monster here, even though it's squashed, or what's the opposite of squashed? Expanded in the horizontal direction. Okay, and this is also interesting. So the monster is only 20 characters wide, but for the small input, we need 24 characters to fill the entire grid, basically. And for the large input, we need 76. And then all those spaces in this string are just for, making it more readable to you. Of course, we have to get rid of all the spaces and line breaks. I do that here, and then finally we convert to a regular expression Java pattern. Okay, cool. So that's that. So, and how are we going to use these regexes exactly? We are going to replace them. So you can not only look for regular expressions once or multiple times, you can also replace them. And if you replace a regular expression containing groups, like this one, then we can say in the replacement, the first group should simply be copied, and then I want a dot instead of the pound sign, then I want the next group, then I want another dot instead of this pound sign, and when we have multiple pound signs, of course, I have multiple dots here. Okay, so basically this submerges the monster because it is replaced with normal water now, if you will. And note again that this is any character in a regular expression, and this is just a literal dot in the replacement. Okay, great. And then here's the main code for part 2. What do we do? So similar to before, just a little more readable. We start with a large input, pass the tiles, and then mapcat the symmetries over that. Okay, so that's nothing new. And then what do we do with all those tiles? We assemble the grid, then we assemble the image, and then we replace the monster by submerging it. Okay, so that's how we do that. Okay, and then we filter for the pounds. We're simply supposed to count them after removing the monsters, and that should give us the right number. But unfortunately, when we execute this, we get the wrong number. So it doesn't matter if we call the replacement for the monsters or not. We always get the same number. So something's still missing here. What are we missing? So let's see. If you remember the assemble grid function, let's look at that again. It starts somewhere in our tiles, namely at the front, at the beginning, right? At the first element. So it starts at a non-rotated, non-flipped tile. But in the final output, the monster can appear itself flipped, right? It could be flipped 90 degrees to the left or 180 to 70, rotated or then flipped. Yeah, and instead of building 8 regular expressions or rotating the final output image, I decided I already have code that is dedicated to symmetries. Why don't we make use of that? So instead of using the first tile that comes out of this function, we could also start with the second tile. I could simply say rest, then we cut off the first symmetry and don't use it. Let's see what happens. We still get 1919, and if we call rest again, we get 1739. That looks rather promising. Okay, cool. So that's a bit, it's not really beautiful to hardcode those two rest calls here. Okay. Unfortunately, 1739 is not the correct solution. If we apply this function again, we get a different number. And how is that possible? Shouldn't string replace all instances of the monster? And that gave me quite a hard time. So the problem is that the regular expression spans multiple lines, and after the replacement, the regex engine will start or continue here looking for monsters, when it should continue here, right? Because we could have 2 monsters swimming right next to each other. And those second monsters won't be found. That's why we have to do it again. And I guess in bigger inputs, maybe we would have to do it a third time. I'm not really sure. Okay, so we get 1649, and that's correct. And if we call the function again, the result stabilizes. Okay, So how could we make this a little more beautiful without hard coding? We need to call rest 2 times, and we need to call string replace 2 times. Maybe let's start here above. So maybe let's get rid of the rest calls again. Okay, and let's say up until this point we have one sequence of tiles containing all the 8 symmetries of the first tile. Why don't we simply make 8 different sequences where every sequence is missing one symmetry compared to its predecessor? And we can do that by saying iterate next. You remember that hopefully from last time where we said what is iterate next of hello, for example. So we start out with a complete value, then the first element is missing, then the second element is missing, third one, fourth one, and fifth one, and then we get a bunch of nils because there's nothing to cut off anymore. Okay, so we can iterate next over that again. Then we have a nested sequence of ever slightly smaller sequences, and we're only really interested in the 8 first 8 of those, right? So we cut our infinite sequence and only take the first 8. Okay, now we have nested sequences, and if we replace the let with a for, then we iterate over those 8 and then basically execute this code 8 times, and we should get a lazy sequence of 8 results. Let's see. Yeah, here you can see it. So the first 2 weren't really that fruitful, the third one was good, and the last 5 were again not successful in finding and replacing any monsters. Okay. Cool, so that already works. So how about this one? How can we, get rid of the second call? How can we say this code should be repeated again and again until the result stabilizes, basically? Right? So in a perfect world, Clojure would have a fix function, but it doesn't have it. So we have to write that fix function ourselves. So let's do it. So let's say fix is a function that takes a function and a starting value. Then we say we apply the function to the value, y equals f of x. We all learned this in school. And then we simply check if the result has stabilized. So if the input and the output are the same, then we can say, right, it doesn't really matter if we return x or y. And otherwise, we have to fix f and y. So y becomes the new f. And of course, we can use tail call optimization here. That should work. Okay, let's see if we now execute this. Yeah, then we get 1649 as before, so we don't use the second call. Perfect. And then, of course, we only want one result, and we can do that by applying the min function, and then we get 1649. Yeah, cool. So this was quite hard. It took me several hours to solve this problem, especially part 2. I guess I didn't write the most efficient version, right? So let's see, assemble grid. So all those edge finding always has to consider, or even those find neighbor functions always have to consider all the tiles. That's probably can be done more efficient with some hash tables or something. Yeah, and even this most outer loop here. Basically, I compute the grid and the image 8 times. That's unnecessarily expensive, but if we look at the final execution time, then that's okay. It's just, not even a fifth of a second. Okay, so as always, I'm very curious how you solved this problem. How hard did you find it? How many hours did you spend? Did you apply any cool algorithms that I overlooked? Let me know in the comment section below.